In this video, we're going to look at the relationship between delta G naught, and the reaction quotient Q. To remind you, delta G naught is the standard free energy change at 25 degrees Celsius. That means any gases are at 1 atmosphere of pressure, all liquids are pure liquids, all solids are pure solids. The elements will be the most stable allotropic form at 1 atmosphere and 25 degrees Celsius, and the solutions are all 1 molar in concentration. The relationship between delta G naught, and the reaction rate quotient is given by this equation. There are two delta G values in this equation. The first delta G value is the delta G anytime. The second delta G is delta G naught. That is the delta G only at standard conditions. This equation is useful because there are actually very few chemical reactions that are occurring at standard conditions. What this equation allows you to do is take the delta G value under standard conditions only and then adjust it for the conditions of the reaction you're actually looking at. So you get to adjust it to non-standard conditions by accounting for the ratio of the concentration of the products and the reactants in Q. What this means is that now you can calculate delta G for reactions that are not under standard conditions. So you can determine the spontaneity of any chemical reaction, not just chemical reactions where the concentration of the reactants are 1 molar or the pressure of the gas is 1 atmosphere. You can calculate it for any concentration because you can calculate Q in non-standard conditions. Let's look at an example chemical reaction and calculate, is this reaction spontaneous under standard conditions? And then look again, is this reaction spontaneous under new non-standard conditions? So first we'll start with the standard conditions. Here's a chemical reaction, and notice that the reactants are all, the reactants and the products are all under standard conditions. We have 1 atmosphere of pressure of hydrogen gas, the solid iodine is pure, and we have 1 atmosphere of HI gas. To calculate if this reaction is spontaneous or not, we simply subtract the delta G of formation values of the products minus the reactants. When we perform this calculation, we find that the delta G for the reaction is 2.6 kilojoules per mole, a positive quantity, and the reaction is not spontaneous. So under standard conditions, this reaction is non-spontaneous. Let's look at this reaction again in the second scenario where we are no longer under standard conditions. Notice that here I've increased the hydrogen pressure from 1 atmosphere to 4 atmospheres. So this reaction is no longer under standard conditions, but we still want to calculate, is this reaction spontaneous? Remember in the previous slide we found that the reaction is non-spontaneous under standard conditions. To calculate if this reaction is spontaneous under these new non-standard conditions, we use the equation delta G is equal to delta G naught plus RT ln of Q. Let's start by reminding ourselves what Q is. Q is the reaction quotient, and it's the concentration of products over reactants raised to their appropriate stoichiometric coefficients. So for this particular reaction, the product is HI gas, and it has a stoichiometric coefficient of 2, and the reactants are H2 and I2. So let's plug in the values we have based on the problem. We know from the previous calculation that delta G naught for this reaction, that's the delta G under standard conditions, is 2.6 kilojoules per mole. We add to that the gas constant times the temperature times the natural log of the reaction quotient, so 1 squared divided by 4. After you perform this calculation, you find that the delta G for the new non-standard conditions is negative 0.8 kilojoules per mole. We found in the previous slide that this reaction is non-spontaneous under standard conditions. But here, where we've increased the concentration of the reactants, we've converted that reaction to be a spontaneous reaction under non-standard conditions, specifically when there's 4 atmospheres worth of hydrogen gas present.